A dark world travels alone. It's a rogue planet, an orphan cast out from its star. And these wanderers aren't rare. They might actually outnumber every star in our galaxy. A silent majority, drifting unseen. A planet without any sun, how does it survive? What hidden oceans might churn beneath that frozen surface? It means a world that truly belongs to the darkness. And the idea of home, it might be in the most unexpected places. Liberated from gravitational bondage, that's a powerful way to put it. A rogue planet doesn't orbit a star. It doesn't circle a sun, not like Earth or Mars. It's a free agent, a solitary traveler. Its path is set by the immense gravity of the galaxy itself. It orbits the galactic core directly. One tiny speck in a vast, slow dance around the center of the Milky Way. That independence defines everything. There's no sunrise. No sunset. Only perpetual night. There are no seasons, no tilted axis pointed toward a distant star. The only warmth comes from within, from the lingering heat of its own violent birth, or from the slow radioactive decay in its core. That makes it fundamentally different from everything in our own solar neighborhood. It's not a comet, a visitor from the outer system, swinging close to the sun on a long elliptical path. It's not an asteroid, a rocky remnant left over from the solar system's formation. And it's not a dwarf planet like Pluto, which, even small and distant, is still bound to our sun's gravity. A rogue planet answers to a much larger master. But the definition can get a little blurry, especially at the upper limits of size. Some of these wanderers are so incredibly massive, they begin to challenge the line between a planet and a star. If an object is massive enough, roughly 13 times the mass of Jupiter or more, the pressure and heat in its core can become so intense it briefly ignites a special kind of nuclear fusion. It starts burning deuterium. That's a heavy form of hydrogen. That doesn't make it a full-fledged star like our Sun, which burns regular hydrogen in a stable, long-lasting process. Instead, it creates what astronomers call a sub-brown dwarf, a faint, failed star. It glows dimly for a relatively short cosmic time before cooling back into darkness. So when we talk about rogue planets, we're talking about a spectrum. Dark, lonely worlds, from those that might resemble a super-sized Jupiter to those that are almost stars. Understanding that fundamental identity, that's where the mystery truly begins. If a world has no sun, what becomes of it? What strange forms of survival might emerge in that endless, starless cold? The journey into darkness starts with a violent goodbye. To become a cosmic orphan, a world has to be torn from its home. That's the main story for most rogue planets. It happens in the chaotic nurseries where stars and planets form. Inside a young solar system, everything is moving. Dozens of protoplanets, large bodies of rock and gas. They're all jostling for position. Their orbits are unstable, shifting. It's a gravitational free-for-all. In that environment, a close encounter isn't a near miss, it's life-altering. Picture a young world, maybe a young Neptune, drifting too close to a massive gas giant. A sibling many times its size. That giant's immense gravity doesn't capture it. It acts like a slingshot. In a precise gravitational dance, the smaller world steals a tiny bit of orbital energy. It gets a boost so powerful it reaches escape velocity. And in an instant, it's flung out of the system, like a stone from a catapult. Destined to wander the galaxy alone, that's cosmic pinball on the grandest scale. But stellar nurseries aren't the only source of chaos. Sometimes the architecture of a star system holds the seeds of its own destruction. Take a system with two stars. A binary pair orbiting each other. Planets can form in stable orbits around that dancing duo. But if one of those stars reaches the end of its life, if it goes through a violent change into a red giant, or even explodes, that delicate gravitational balance shatters. The sudden loss or change of mass sends shockwaves through the system. Orbits become wildly unstable. Planets can be thrown into each other, or more often, they're just ejected into the void. Their sun, or one of their suns, it essentially vanishes from their sky, leaving them adrift. That violent birth points to a fundamental truth about planetary systems. Stability isn't a given, it's a prize, won through a delicate arrangement of masses and distances, and not every world is fortunate enough to secure it. For every Earth, nestled in a calm, circular orbit, there may be countless others that lost that gravitational lottery, cast out in the system's turbulent youth, to become permanent citizens of the interstellar dark. Some wanderers, their story is different. Their loneliness doesn't start with a violent separation. It starts with a quiet, solitary birth. A place far from the busy nurseries of stars, the darkest, coldest parts of space, where vast clouds of gas and dust drift. Molecular clouds, the raw material. Inside them, small pockets can grow dense enough to collapse under their own weight. Gravity pulls the material in. It starts to spin, to flatten, to grow warm. But in this remote corner, there isn't enough material. The clump isn't massive enough. It can't cross that critical threshold. It can't ignite the sustained nuclear fusion to become a star. So what happens to it? It may just coalesce into a sphere, a ball of gas and rock, a planet-sized object that forms directly from the cloud, free-floating from the very start. It never had a sun to lose. It has always known the dark. That's a profound shift. It means planets aren't just byproducts of star formation. They can be primary products. They can form on their own through the same process, just smaller. This challenges the old idea, the nebular hypothesis, that all planets form from the leftover disk after a star is born. Here, there is no leftover disk. There is no central star. There's just the cloud and the planet it makes. These would be primordial wanderers, worlds that have never felt a star's warmth. Their composition could be a direct snapshot of the pristine interstellar medium, untouched by the heat and chemistry of a stellar nursery. They are, in a sense, pure. Untethered from the beginning, this theory opens a new chapter. It suggests a hidden population of worlds born from solitude, destined for solitude. A silent, ancient tribe that has wandered the galaxy since the earliest times. Their existence asks a fundamental question. What is a planet, even? Is it defined by orbiting a star, or is it defined by how it came to be? Hundreds of billions. That's the estimate. For our galaxy, these dark wanderers, a number that big, it changes what normal is. For every star you can see, there might be dozens of planets. Maybe hundreds, just drifting between them, unseen. They're the silent majority, a ghostly background woven right into space. This isn't a few lost worlds. It's a hidden ocean, and our solar systems, the ones with suns, they're just islands in it, scattered. So how do you count something that dark, that distant? There's a trick, a gravity trick, microlensing. If one of these rogue planets drifts exactly between us and a distant star, its gravity bends the light. Acts like a lens. The background star gets brighter for a few hours, a few days, it flares in the data, then it fades. That flicker is the signature. An invisible mass passing by, it leaves no other trace, no light. Just a momentary distortion in spacetime. That's how you see it. Astronomers scan millions of stars. They count these rare flickers, build a census from statistics, and the numbers point to something. Planetary ejection, it's not a rare accident, it's common. Maybe inevitable, for most young solar systems. Chaos and gravitational scattering, that's the rule, not the exception. Our stable neighborhood here might be the outlier. The cosmic exception, that changes the whole picture of galactic architecture. We used to think of galaxies as stars with their planetary families. Now you have to see it differently. A vast sea of dark, nomadic worlds, and the stellar systems move through it. A galaxy where planets are the most numerous large objects, not stars. It suggests a hidden landscape. A gravitational one, shaped by all these drifting masses. Their combined pull is subtle, but it might gently shepherd star clusters or influence orbits. Way out at the edge of our own system, comets maybe, They're like the dark matter of worlds, unseen but ever present, and it forever changes what home looks like. Einstein gave us a way to see the invisible. He said massive objects bend spacetime, and light follows that curve. So a star, a planet, it can act like a lens. It can magnify something behind it. That's a gravitational lens. On a cosmic scale, it's a telescope built by gravity. But for a single rogue planet, the effect is very small. A microlensing, that's how we find these dark worlds. It needs a perfect alignment, a distant star, a rogue planet drifting in the dark, and our line of sight from Earth. All three have to line up. When they do, the planet's gravity warps the space around it. It focuses the star's light toward us just for a moment. From here, the star doesn't just get brighter. It brightens in a specific way, it flares, it peaks. Then it fades symmetrically as the alignment passes. That light curve is the signature, the ghost's fingerprint. The duration of the flare tells us the mass. An Earth-mass planet might cause a brightening that lasts only a few hours. A Jupiter-sized one could last for days. It's a delicate measurement, a whisper of gravity recorded across light years. But catching that whisper takes patience. You're looking for a single flicker among hundreds of millions of stars. It's like watching a field of nightlights, waiting for one to briefly glow brighter. You can't predict where or when, so you have to watch everything all the time. That's the work of projects like OGLE and MOA. They use powerful telescopes to stare, night after night, at the densest star fields toward the galactic bulge. They're not looking for planets orbiting those stars. They're using the stars as a backdrop, a vast screen of light sources, hoping a dark wanderer will pass in front and betray itself. Every flicker in the data is a candidate. Each one has to be verified, analyzed, to rule out other causes like stellar flares or instrument error. It's detective work. Piecing together the existence of a world from a single, transient curve of light. This method finds rogue planets. It finds the small ones, the Earth-mass wanderers, which are nearly impossible to detect any other way. It reveals the true population of the dark. And every confirmed detection is a small miracle of alignment, a fleeting conversation between a lost world, a distant sun, and a watchful eye here on Earth. For the youngest and the most massive of these planets, there's another way to find them. Sometimes you can see them directly, not by their shadow but by their own light. A faint, dying light. Think of a world just born, a huge ball of gas many times the mass of Jupiter, fresh out of a collapsing cloud. That formation process, it releases a huge amount of gravitational energy. It heats the young planet from the inside, and for a brief time, maybe a few million years, it glows. It radiates a deep, ruddy heat in the infrared. It's a cooling ember in the dark. That faint glow, that's the key. It means the planet isn't completely invisible. To our most advanced telescopes, it's a dim, warm speck against the cold of space. This is where something like the James Webb Space Telescope comes in. With its incredible sensitivity to infrared light, it can look into those chaotic nurseries where stars form. Places like the Orion Nebula, the Sigma Orionis cluster. In these dusty regions, it can search for pinpricks of warmth that aren't attached to any star. The challenge is huge. You have to separate that one faint point of heat from the brilliant glow of newborn stars nearby, and from the warm infrared haze of the nebula itself. It's like trying to spot a single candle's flame from across a city while you're standing in the middle of a bonfire. But when it works, the reward is profound. Direct imaging gives you more than a statistical blip. It gives you a portrait. Astronomers can take the light from that faint glow. They can break it apart into a spectrum. And from that spectrum, they can learn about the planet's atmosphere. What gases are there? The temperature of its outer layers. Maybe even hints of clouds or weather patterns in that eternal night. This method is a beautiful complement to microlensing. Microlensing tells you how many are out there and finds the small ones, the old ones, the cold ones. Direct imaging lets you study the young giants up close, lets you understand their chemistry, their birth conditions, Together, they sketch a fuller picture of this hidden population. From the ancient, frozen Earth, mass wanderers you only see through gravity's lens, to the infant gas giants still glowing with the heat of their own creation. Each method shows you a different chapter in the story. The story of the galaxy's lost worlds. A world without a sun doesn't have to be a cold world, it can survive. It has its own fire inside, an internal furnace. The main heat for a rogue planet comes from its own interior, and that's two things working together. The first is leftover heat from when it formed. When a planet comes together from dust and gas, particles collide and compress. That gravitational energy turns into heat. It's like rubbing your hands together, but for a whole planet. That heat gets trapped inside. It's a kind of birthright, and it takes billions of years to slowly leak away into space. The second source is radioactive decay. Deep in the rocky core, elements like uranium and thorium and potassium, their unstable atoms break down. They release energy as heat. It's not an explosion, it's a steady trickle. A natural reactor buried under miles of rock and ice. For a big gas giant, this internal warmth is strong. It can hold onto a thick atmosphere for eons, so it doesn't just freeze into a ball of ice. That atmosphere could have complex cloud layers churned by winds. Winds driven not by sunlight, but by the difference between the warm inside and the frozen surface. The weather there would be a permanent global storm, powered from below. But for smaller, rocky worlds, this internal furnace changes everything. Think of a rogue planet about Earth's size. Its surface is a frozen wasteland. Maybe 250 degrees below zero, lit only by starlight, but you drill down, you go deep, the pressure builds, the heat from the core starts to rise. At a certain depth, the temperature could get past the point where water stays liquid. That creates a possibility, a subsurface ocean, a huge, dark sea, sealed under a global shell of ice kilometers thick. It's a hidden reservoir, kept liquid not by a sun but by the planet's own heart. That idea changes what a habitable place could be. We talk about the Goldilocks zone, that narrow band around a star. But a rogue planet makes its own Goldilocks zone, not around a star but around its own core. The heat for chemistry, for geology, comes from within. In that subsurface ocean, geothermal vents on the seafloor could spew minerals and warmth into the water. Places of huge energy and chemical complexity, even in total darkness. On Earth, we find whole ecosystems around deep sea vents, completely cut off from sunlight. They run on chemosynthesis, using chemicals from inside the Earth. A rogue planet's hidden ocean could, in theory, be a similar haven. A place where the ingredients for chemistry, maybe even for life, could find a way. It means the loneliest worlds in the galaxy might not be empty. They could be dark, silent arcs, carrying hidden seas through the interstellar void. That hidden sea is the fifth mystery. The possibility of an abyss and what could be down there. On a rogue planet, a subsurface ocean wouldn't be a small thing. It would be a global feature. A single body of water, wrapped around the rocky core, sealed under an ice shell that could be dozens of miles thick. We see hints of this in our own solar system, on moons like Europa and Enceladus. But there, the oceans are kept liquid by tidal forces, the gravitational squeezing from their giant parent planets. A rogue planet has no such neighbor. Its ocean relies on a different warmth, the planet's own internal heat, that steady, geological warmth from radioactive decay and leftover formation energy. A quieter furnace, and it could be enough. But what if that heat gets a boost? Tidal heating doesn't need a permanent star. It just needs a gravitational dance. If a rogue planet captured a moon or formed with one, the push and pull between them could generate friction inside the planet. That friction turns into heat, pumping extra energy into the hidden ocean. Even a rare, close encounter with another star during its journey could provide a temporary but intense period of tidal warming, stirring the depths for millions of years. These events could reignite geological activity, cracking the ice shell, renewing the ocean's chemistry. It means these dark worlds might have active chapters, brief periods of heightened potential. Down in that eternal dark, under immense pressure, the stage could be set. On the seafloor, where the rocky mantle meets the water, hydrothermal vents would likely form. These are cracks in the planet's crust, where mineral-rich water, superheated by the interior, gushes back into the ocean. On Earth, such vents are oases. They're not just geysers of hot water. They are complex chemical reactors. The hot fluid carries dissolved minerals like sulfides and iron from the rocks below. When this fluid hits the cold ocean water, those minerals precipitate out, building towering, chimney-like structures. More importantly, that chemical disequilibrium, the difference between the vent fluid and the ocean, provides an energy source. This is chemosynthesis, life's alternative to photosynthesis. Instead of using sunlight to make sugar, organisms use chemical energy. On Earth, entire ecosystems thrive around these vents, completely independent of the sun. Giant tube worms, blind shrimp, strange bacteria, all sustained by the planet's internal heat and chemistry. A rogue planet's ocean could offer the same three ingredients we think are crucial for life. Liquid water, a universal solvent, a source of energy from chemical reactions at the vents, and organic chemistry, the building blocks that could form in that warm, mineral-rich soup. The abyss wouldn't be a barren pit. It could be a sanctuary. This changes the entire idea of the rogue planet. It moves it from cosmic debris, a dead rock adrift, into perhaps one of the most promising places to look for life in the entire galaxy. The challenge, of course, is staggering. That protective ice shell is also a perfect barrier, hiding all evidence from the outside universe. Any biosphere down there would be utterly isolated, evolving over billions of years in complete darkness, unaware of stars, galaxies, or any universe beyond its icy ceiling. Finding it would require not just looking, but listening for whispers in the dark, or dreaming of a day we could pierce that frozen shield. The loneliest place imaginable might just be where the galaxy hides its most resilient secrets. The weather on a rogue planet has no memory of a sun. Its atmosphere is a closed system, a cloak of gas held by gravity, stirred by one deep source of warmth. The planet's own internal heat. Without a star, the idea of a day just breaks down. No sunrise to warm the air, no sunset to cool it. The only real temperature difference comes from within. Heat from the core seeps up, trying to escape into space. That creates a constant gradient. The atmosphere is warmest near the surface, where it touches the ground or an icy shell, and it gets colder as you rise into the eternal night sky. This internal furnace drives everything. The air circulation wouldn't be a fast system like Earth's, powered by the sun. It would be slower, more deliberate. A global convection, like a pot on a low simmer. Warm air would rise from the warmer equatorial regions, then flow high in the atmosphere toward the cold poles, where it cools, sinks, and flows back along the surface. A single, planet-wide sigh repeating over eons. The winds might be relentless, but also strangely gentle. A slow-motion river of gas flowing from the planet's warm belly to its frozen skin. And what falls from those dark skies? Not water rain. The surface is far too cold. Instead, the atmosphere might condense into exotic snows. If the planet is cold enough with the right chemistry, gases like nitrogen or methane could freeze right out of the air. A slow, silent snowfall of nitrogen flakes, drifting onto a landscape already covered in mountains of that ice. Or a methane blizzard, where the snow evaporates before it hits the ground, creating a perpetual, ghostly haze. The weather would be a frozen, silent ballet, lit only by the faint glow of the Milky Way or the distant flash of a passing star. It's a stark contrast to planets with suns. Earth has hurricanes, thunderstorms, seasons. A rogue planet has a permanent deep freeze, punctuated by slow atmospheric tides and the gentle fall of alien ice. Its weather isn't about change, it's about equilibrium, a forever state, balanced between the heat leaking out from below and the absolute cold of space pressing in from above. It's the climate of deep time, unchanging and patient. What happens when a world is left entirely to its own devices? A rogue planet's journey doesn't have to be completely solitary. A world cast out into the dark might still find a companion. That's the sixth mystery, the possibility of wandering moons. Could a planet without a star have its own satellite? The answer is yes. Gravitational capture is the key. During the chaotic ejection from its home system, as a young planet is flung away, it might tear a smaller sibling along with it. That moon would be ripped from its own orbit, becoming a permanent captive, bound to the rogue planet as they both sail into the void. Or later in its galactic travels, the wandering world might pass close to a lone asteroid or even a smaller rogue planet. If the encounter is slow and precise, the larger world's gravity could snare the smaller one, pulling it into a new orbit. This creates a binary system, two dark bodies locked in a mutual dance, forever adrift together. The moon would have no reflected sunlight to see by. Its only illumination would be the faint, ruddy glow of the primary planet's internal heat, if it's a gas giant, or perhaps the shimmer of auroras in a thin atmosphere, sparked by charged particles from space. For the moon itself, this partnership could be transformative. The constant tug between the two bodies creates tidal forces. As the moon orbits, the planet's gravity stretches and squeezes its interior. This friction generates heat, a process called tidal heating. On a cold, dead rock, this could be the difference between a frozen tomb and a geologically active world. That internal heat could maintain a subsurface ocean, much like the one on the primary planet. It could drive volcanic activity on the surface, renewing the crust and releasing gases that might form a thin, temporary atmosphere. The energy from this dance could create a stable, warm pocket in an otherwise frigid moon. It adds a layer of complexity. The primary rogue planet, with its own internal furnace, now has a partner that is also warmed from within, not by radioactivity, but by their shared motion. They become a coupled system, a tiny, dark solar system of their own, providing energy and stability to one another on an endless journey. Their gravitational interaction might even help stabilize any axial tilt, preventing wild climate swings and creating a more consistent environment under the ice. So the image shifts again. It's no longer just a single speck of darkness, it could be a pair, a binary world circling each other in the silent black, holding onto a fragment of connection. Their dance is a private source of warmth and change, a hidden engine powering possibilities in the perpetual night. It follows a grand, silent arc around the galaxy's heart. A rogue planet doesn't orbit a star, but it isn't free. It's still held by the Milky Way's immense collective gravity, so it moves not in a circle around a sun, but in a vast, slow ellipse around the galactic core. An orbit around nothing and everything all at once. A single journey can last hundreds of millions of years, a timescale that defies imagination. For most of that voyage, the planet sails through near total emptiness, the interstellar void. But its path isn't straight. It's a galactic itinerary written in gravity. That path can take it through profoundly different neighborhoods. It might plunge inward through the crowded stellar city of the galactic bulge, where stars are packed tightly together, their light a perpetual dim glow. Here, the planet would navigate a dense forest of suns, though the distances are still so vast that direct collisions are almost impossible. Or its orbit might carry it high above the galactic plane, into the sparse and ancient stellar halo, a realm of lonely, old stars and dark matter. Or it could sweep through one of the majestic spiral arms, where star formation is active, passing brilliant young clusters and glowing nebulae. Each leg of the journey changes the environment. In the bulge, the planet would be bathed in a higher background of radiation from all those nearby stars. In the spiral arms, it might pass close to a supernova remnant, feeling a surge of cosmic rays. These exposures could alter the chemistry of its upper atmosphere, or even affect the radiation reaching a subsurface ocean, acting as a rare source of external energy. But the most dramatic changes come from chance encounters. Every so often, across those millions of years, its path might bring it close to another star or a dense molecular cloud. Gravity is the great sculptor. A close pass by a star is like a gentle nudge from a cosmic giant. It can bend the planet's trajectory, altering its orbit around the galaxy, speeding it up or slowing it down. A course correction on a galactic scale. And in the rarest possibility, that stellar encounter could be so precise, so slow, that the star's gravity captures the wanderer. After billions of years of solitude, the rogue planet could be pulled into a new orbit around a foreign sun. It would become a planet again, in the traditional sense. A captured world, joining a family it was never born into. Its surface, frozen for eons, would suddenly feel the warmth of a new star. The ice would begin to melt, the chemistry would awaken. A second birth. A planetary resurrection after an epoch of darkness. This possibility means the population of planets in orbit around stars might not be static. Some could be adopted, immigrants from the dark spaces between the stars. Our own solar system in its distant past might have captured such a wanderer, incorporating it into our strange family without ever knowing its true, lonely origin. The galaxy is a place of endless journeys and second chances, even for worlds that have been lost. That lonely path, it turns it into more than just a wanderer. It becomes an interstellar vehicle, a natural starship, and the seventh mystery asks what a world like that could carry between the stars. We've seen interstellar visitors before, like Oumuamua and Borisov, but those were small fragments moving fast. A rogue planet is a different scale of traveler. It's vast, it's slow, and it carries its own environment with it. If one passed through the outer solar system, it wouldn't look like a streaking comet. It would look like a new, faint planet. Astronomers tracking it would notice something strange about its motion. Its path would be hyperbolic, an open curve, not the closed ellipse of a world bound to our sun. It would be a slow, majestic intruder, moving against the stars with its own purpose. Its passage wouldn't be silent. Its gravity, however faint, would ripple through the frozen outskirts of our system. It would brush against the Oort cloud, that distant shell of icy bodies from the solar system's birth. The gentle tug of a passing planetary mass could dislodge thousands of those dormant objects, nudging them onto new paths that fall inward. It could trigger a shower of new comets, an event that would unfold over thousands of years after the wanderer had left. It's a reminder the galaxy isn't static. The space between stars isn't empty. It's a highway for dark, massive travelers, and their gravity can stir the depths of other solar systems long after they've gone. That leads to a profound idea, even if it's speculative. Could a rogue planet be a carrier, a natural ark? Its thick ice shell, its hidden ocean, they could preserve material for eons, shielded from radiation in the deep freeze of space. If life ever arose in that subsurface sea, that entire biosphere would be traveling with it, completely self-contained. As it drifts for billions of years, it might eventually pass close to a young, stable star system. If captured, that ice shell could begin to melt. The chemistry of that ancient, protected ocean would be introduced into a new, warm environment around a new sun. The building blocks for life, or maybe life itself in a dormant state, could be delivered from one stellar neighborhood to another. This concept is called panspermia. It suggests life might not always originate where we find it. It could be a galactic traveler, using planets as its vessels. On the longest timescales, these dark worlds could be the great connectors of the galaxy. Not through intelligence or design, but through simple, patient motion. They are the slow boats crossing the cosmic ocean, potentially carrying the seeds of chemistry or biology from shore to distant shore. They challenge the idea that each star system is an isolated island. Instead, they paint a picture of a galaxy that's subtly, slowly exchanging material across the vast voids. The most desolate object we can imagine, a frozen world without a sun, might be the most important courier in the history of the cosmos. We've reached a kind of boundary. A line in the cosmic fog, The difference between a planet and a star, it isn't always sharp. At the highest masses, a rogue object starts to change. It becomes something else. A brown dwarf. Astronomers sometimes call them failed stars. They form like stars from a collapsing gas cloud, but they never gather enough mass to cross that critical line. They can't sustain stable hydrogen fusion, not like our Sun does, but they aren't completely cold. For a brief time, if they're massive enough, around 13 times Jupiter's mass or more, the pressure and heat in their core can ignite a different, fleeting fire. They can burn deuterium, a heavy isotope of hydrogen. It's a short-lived process, maybe just a few million years. Then the deuterium runs out, and the object slowly cools into darkness. So where does the planet end and the brown dwarf begin? It's a question of formation and physics. An object above that 13 Jupiter mass line, whether it orbits a star or drifts alone, is usually called a brown dwarf. It belongs to the stellar family, however small. Below that line, we're in the realm of planets. Objects that form in disks around stars, or as we've talked about, sometimes in isolation. But nature doesn't respect our neat categories. There's a continuum, a smooth gradient from the most massive gas giant planets, through these substellar brown dwarfs, and up to the smallest, dimmest true stars. And the population of free-floating objects spans this whole range. We find lonely giants that are clearly planets, and we find isolated, cooling brown dwarfs that are almost stars. Studying them together is crucial. They represent the lowest mass outcomes of the star formation process. It's a frontier we're still mapping. By comparing a rogue planet, a super-Jupiter, to a low-mass brown dwarf of similar age, astronomers can ask fundamental questions. Did they form the same way? Does a 10-Jupiter mass object that formed alone in a cloud have a different internal structure, a different atmospheric chemistry, than one that formed in a disk around a star and was later ejected? The answers help us understand the rules of assembly. For the smallest objects in the cosmos, it shows that the galaxies' dark wanderers aren't one kind of thing. They're a spectrum, lonely orbs from frozen, Earth-sized worlds to fading embers of failed suns, all sharing the same endless night. Even the loneliest wanderers can find a partner. The eighth mystery is the free-floating binary. Two orphaned worlds, not just one. A pair of planetary mass objects, bound by their own gravity, orbiting a common center of mass in the space between stars. A miniature solar system with no sun. Their origin is delicate. They might have formed together from a tiny, isolated pocket of a molecular cloud, a double planet from the start. Or, more dramatically, they were both part of a larger planetary family around a star. During the chaotic gravitational scattering that ejected them, their mutual bond held. They were flung out together as a single unit. That survival is the puzzle. The forces that eject planets are violent, chaotic slingshots. For two objects to remain tied after that speaks to an incredibly stable, close initial orbit. It's a testament to resilience. Certain gravitational arrangements can hold even in stellar-scale turmoil. Finding such a system would be a prize. We could observe their mutual dance. By timing their orbits around each other, astronomers could apply Newton's laws directly. The period of their orbit and the distance between them would reveal their combined mass. With beautiful precision, it's one of the few ways to get a direct, unambiguous measurement of a rogue planet's mass. Not an estimate. That data is a key. It unlocks their interior composition, their true nature. Imagine it. Two dark spheres, one perhaps larger than the other, silently circling in perpetual night. Their only light is the faint infrared glow of their own residual heat, and the distant backdrop of the galaxy's stars. They provide each other's only consistent gravitational influence. A private clockwork mechanism, ticking away in the infinite quiet. Their existence suggests companionship, even in the deepest isolation, might be more common than we thought. It expands the catalog of what's possible in the interstellar dark. Not just solitary nomads, but pairs, couples on an endless shared journey, holding onto each other against an uncaring galaxy. The story of these wanderers isn't only about the giants. There's another kind of rogue, a terrestrial world about the massive Earth, a frozen marble of rock and iron. That's the ice world archetype, a planet like ours in size and composition, but cast out early in the gravitational chaos. Its fate is a deep freeze. A permanent one. Without a sun, the surface temperature drops to just a few tens of degrees above absolute zero. Any atmosphere it had wouldn't last. The gases would freeze solid, collapsing into glaciers. Glaciers of nitrogen, oxygen, carbon dioxide ice. Or they'd be stripped away slowly by the thin interstellar wind. Leaving the surface exposed to the vacuum of space, the landscape would be still, profoundly desolate. Mountain ranges of water ice hard as granite over plains of frozen air. Ancient impact craters would stay perfectly preserved. No weather to erode them, no wind, no rivers. The only movement might be the creep of the ice. An imperceptibly slow creep over geological epochs. A glacial pace on a world that is itself a glacier. Beneath that frozen crust, the story is different but equally still. Without a massive gas giant for tidal heating, the interior of this rocky world would settle. Its geological heartbeat would slow and then stop. The mantle would solidify. Volcanic activity would cease. The core, a sphere of molten iron, might still be liquid, trapped by the insulating pressure of the rock above. But it wouldn't drive a magnetic field anymore. The planet becomes geologically dead, a fossil world, yet inside that fossil is a record, a priceless one. Its chemical composition is a direct snapshot. A snapshot of the stellar nursery where it formed, the isotope ratios in its rocks, the specific mix of metals in its core, even the possible presence of certain radioactive elements. These are all fingerprints. They tell the story of the particular cloud of gas and dust, the cloud that birthed its original star and planetary family. That makes a frozen terrestrial rogue more than a lost world. It's a time capsule, sealed in the perfect cold of interstellar space. An asteroid or comet in our own solar system has been altered. Altered by billions of years of solar heating, radiation, collisions. Its record is scrambled, but a rogue terrestrial planet, frozen since its ejection, is pristine. Its chemistry is locked in time, locked from the moment it was thrown out. If we could ever retrieve a sample from such a world, it would be like opening a letter. A letter sent from the earliest days of our own solar system's formation. It could tell us about the conditions that existed before the planets finished assembling, offering clues about our own origins, clues that are lost forever on the active, weathered worlds orbiting our sun. The most isolated, silent object in the galaxy could hold the loudest answers. Answers to how planetary families are born. A magnetic field is a planet's shield. It's invisible. For Earth, it's vital. It comes from deep inside, from a molten iron core. The planet spins, and that churning liquid acts like a dynamo. It creates a protective bubble around us. That bubble deflects the solar wind, that constant stream of charged particles from the sun. It preserves our atmosphere. It shields life from radiation. But then you have a rogue planet, a world with no sun, no solar wind, and no clear reason to spin fast. That's the ninth mystery, the magnetic enigma of the rogue world. A rogue planet, a rocky one, follows different rules. It isn't tidally locked to a star. Its rotation isn't forced. It could spin slowly, very slowly. An entire Earth month for one turn, maybe a year. That slow rotation is a problem for the dynamo theory. A dynamo needs motion, vigorous churning to sustain itself. Without a fast spin to drive convection in the core, the currents inside might just settle. They might stagnate. The planetary heart could grow quiet. The magnetic field could fade over billions of years, and the world would be exposed, but the need for that shield doesn't go away. Even in the deep quiet between stars, there's a threat. Galactic cosmic rays, high-energy particles, atomic nuclei accelerated to near light speed by distant supernova. They permeate the galaxy. Without a magnetic field to deflect them, these particles would bombard the planet's surface, or more importantly, the icy shell over a subsurface ocean. They could penetrate deep, breaking apart complex molecules, disrupting any delicate chemistry brewing in the dark water below. A magnetic field is a cosmic umbrella. It diverts that relentless rain. It creates a calmer environment underneath, so the question becomes critical. Could a rogue planet generate a magnetic field another way? One possibility is internal heat. If the core stays hot from radioactive decay, it could drive convection on its own, independent of rapid rotation. Heat rising from the deep interior could create plumes of molten metal. Those plumes rise and cool, then sink again. A slow, heat-driven circulation. That circulation, interacting with whatever residual rotation the planet has, might power a weak dynamo. A different kind of magnetic engine, fueled by internal warmth, not a fast spin. Another source could be chemical. As the core slowly cools, certain elements crystallize out of the molten mix. The process of solidification releases buoyant material. It floats upward, stirring the liquid core again. That's compositional convection. It could provide the necessary motion to sustain a magnetic field long after the planet's initial heat has faded. It's a gentler process, more gradual, but over the eons it might be enough. The presence or absence of this shield has profound consequences. For a rogue planet with a subsurface ocean, a magnetic field could mean the difference between a sterile brine and a protected haven. Where complex chemistry, maybe even simple life, could persist, it would help retain any tenuous atmosphere from the interior. Prevent it from being stripped away by the interstellar medium. It defines the world's long-term character. A magnetically active rogue planet is a world with an internal heartbeat. A protective barrier, holding a tiny pocket of order against the chaos of space. A world without one is more vulnerable, more exposed. A frozen relic, slowly weathered by the galaxy's background radiation. Solving this enigma isn't just about magnetism. It's about understanding whether these loneliest worlds can truly be sanctuaries. Our galaxy is just one island in a cosmic ocean. The physics that makes rogue planets here has to work everywhere. In every spiral galaxy, every elliptical, every irregular one that ever formed stars. So these dark wanderers, they're not just a Milky Way thing. They're universal, and each type of galaxy, with its own history and stellar makeup, would have a different population of these lost worlds. Their story becomes a kind of galactic fingerprint. Think about the big elliptical galaxies. They're older stellar cities where the frantic star formation from their youth has settled down. Their stars are ancient, and so are their planetary systems. In that kind of environment, the violent era of planetary ejection happened billions of years ago. Any rogue planets there would be the coldest, the oldest. They've been drifting through that quiet, red light for eons. Their internal heat faded to almost nothing. They're the ultimate fossils, moving through a galaxy that's itself a fossil of a more dynamic past. Studying them would tell us about planet formation in the universe's early chapters. Now, contrast that with pure cosmic violence, colliding galaxies like the antennae, two spiral galaxies tearing through each other. Their gravitational fields are tangled in chaos. That doesn't just stir up gas to make new stars. It violently shakes the existing planetary systems. Imagine gravitational shockwaves passing through hundreds of billions of star systems. For countless planets, stable orbits become impossible. A fresh wave of ejections on a staggering scale gets unleashed. A galactic collision could produce a sudden surge of rogue planets, a new generation of orphans born from the turmoil. Their populations would be a mix. The ancient wanderers from before the crash and this new cohort, still holding some warmth from their recent birth. This galactic perspective changes things. It means we can't understand rogue planets by looking just at our Milky Way. Their demographics, their numbers, their masses, their temperatures, have to be shaped by their home galaxy's life story. A quiet, aging elliptical and a violent, merging galaxy would create completely different legacies of lost worlds. That elevates them from curiosities. They become potential markers, tracers of galactic history. If we could one day measure the rogue planet population in a distant galaxy, it would tell us a story. About that galaxy's past stability, its history of collisions, the typical outcomes of planet formation inside it. They're a silent record of the gravitational peace, or violence, a galaxy has experienced. They hint at a universal truth. That building planets is inherently messy. That a fraction of the worlds created in any galaxy will always be lost to the dark. Their presence between stars isn't an accident. It's a fundamental, maybe inevitable, part of how galaxies evolve. The loneliest objects might hold the key to reading the biography of their entire galactic home. Exile isn't always permanent. A rogue planet, even after drifting for billions of years, still has a slim chance, a chance for a new home. The galaxy is always moving slowly. Paths cross, that's the recapture scenario, the question of adoption. The math of gravity says it's possible. If a wandering world comes near a star and it's moving slowly enough, the star's gravity can catch it. That open curve, the path of an escape, bends. It becomes a closed loop, a bound orbit. This is more likely where stars are crowded together, in globular clusters. Or the galaxy's central bulge. In those stellar cities, close encounters happen more often. A captured world wouldn't get a nice, circular orbit, not like Earth. Its entry would be messy. It would probably end up on a stretched, eccentric path, a long ellipse from a distant, frozen point to a brief, scorching close pass. Its orbital plane would be tilted too. Inclined, compared to the native planets, it would stand out, an immigrant planet, its motion a strange accent. This idea might explain some of the exoplanets we see. Gas giants in wild, eccentric orbits. Orbits tilted sharply against their star's spin. Some of those could be captured rogues. Adopted long after the system formed, their odd orbits are a signature, a history of loneliness written in their mechanics. The speculation gets closer. To our own solar system, out beyond Neptune, there's gravitational evidence, hints of a large, undiscovered world. Planet 9, they call it, a hypothetical object. Its gravity seems to shepherd some distant icy bodies. It's just a hypothesis, but one theory for its origin is capture, that it's a captured rogue planet. A frozen world, maybe Neptune-sized, that our sun caught early on. It would orbit now on a vast, slow ellipse, a permanent reminder that our planetary family might not be entirely native. That possibility changes the view. Solar systems aren't static portraits. They're dynamic families. Over cosmic time, they can gain members through capture. Or lose them through ejection. A star's planet count isn't fixed at birth. It's a tally that can change across the eons, so a rogue planet's journey has two possible ends. It can wander forever, a monument to solitude, or with cosmic luck, it can find a new sun, new gravitational siblings, and start a new chapter, as a planet with a home. All those dark wanderers out there, it makes you ask a question: could they be the dark matter? For a long time, we've known the Milky Way is too heavy. If you add up all the stars, all the gas and dust, it doesn't account for the gravity we feel. Most of the mass is something else, something invisible. That's dark matter, and we don't know what it is. So, could it be these rogue planets on the surface it fits? They are massive, they give off almost no light. They are dark, and we know now there are so many of them, far more than stars. If each one is about the mass of Jupiter, together, their gravity would be strong. They'd add mass we can't see. It seems perfect for a moment. A hidden part of the galaxy made of normal planetary material just drifting. But then you run the numbers. And the numbers don't work. Even if you take every microlensing event we've ever seen and push the estimates as high as they can go, the total mass of all rogue planets is still just a tiny piece. Dark matter needs to be about 85% of the galaxy's mass. The stars and gas we see are about 15%. And these rogue planets, in the most extreme case, they might be 1% of that 15%. A drop in the ocean, so they're not the dark matter, but that doesn't mean they're nothing. Their importance is different. They show us something. They are normal matter. Baryonic matter, but it's dark, and we've been missing it. When we counted the mass of the galaxy, we counted the bright stars, the glowing gas. We knew some normal matter was missing too. Hidden, rogue planets are part of that. They're a piece of the ordinary universe that's just very, very hard to see. They remind us, in a concrete way, that what shines in the night sky is only a part of what's there. The galaxy is built from light and dark. And even in normal matter, there are whole populations living in shadow. They teach us to look past the light, to measure the universe by its gravity, not its glow. And that sharpens the real question. If all these planets aren't the answer, then what is? The search for these dark wanderers is about to change completely. Our tools are evolving. They're moving from statistical hints toward detailed pictures. A new generation of observatories is coming. Their mission is to map the invisible. Leading this is NASA's Nancy Grace Roman Space Telescope. It's named for the pioneering astronomer. Its key strength is a wide field of view and an infrared eye. That combination is perfect for microlensing surveys, on a scale we've never seen. Current telescopes catch a few of these events by chance. Roman will do a systematic, long-term watch. It will stare at the same dense star fields for months. It will monitor hundreds of millions of stars at once. That relentless gaze should reveal thousands of microlensing events. It will build the first robust catalog of rogue planets. We'll move from knowing they are common to knowing their distribution. How many are Earth-sized? How many are Jupiter-sized? Where in the galaxy they tend to drift? It transforms a mystery into a measurable population. Alongside Roman, there's the European Space Agency's Euclid mission. It adds another layer. Its primary goal is to map dark energy, the force shaping the cosmos, but its deep, wide-field surveys will also capture the sky in exquisite detail. As it scans for the subtle distortions in galaxy shapes caused by dark matter, it will record countless points of light. In that data, astronomers will search for faint, slow-moving infrared dots. Those could be young, warm rogue planets or brown dwarfs. Euclid's contribution will be a vast celestial census. It provides context and candidates for further study. These space telescopes work together. One hunts the subtle gravitational flickers of ancient, cold worlds. The other captures the faint glow of younger ones. On the ground, the revolution continues with direct imaging. The challenge was always the blinding glare of a host star. But for rogue planets, that problem vanishes. There's no star to overwhelm the detector. The new challenge is sensitivity, catching that incredibly faint infrared signature. Future giants, like the extremely large telescope, will use advanced optics to push this limit. One groundbreaking technology is the vortex coronagraph. This isn't a physical mask. It's a special pattern etched into a glass lens. It manipulates light itself. In theory, it can suppress starlight by a factor of millions, but for rogue planets, its precision will be used to analyze the faint light we do collect. By studying the spectrum of a rogue planet's own thermal glow, these instruments could identify molecules in its atmosphere. We might detect methane, water vapor, even signs of complex chemistry in the upper layers of a young gas giant. This turns a pixel of warmth into a world with character. The goal is a new classification. Not just rogue planet, but categories defined by mass, by estimated age, by atmospheric type. Are there carbon-rich wanderers, oxygen-rich ones? Do some show signs of silicate clouds? That would suggest a past sculpted by internal heat. Each piece of data is a clue to their origin story. A planet with an atmosphere like Jupiter's might be an ejected giant. One with a more primordial mix, untouched by a star, could be a free-floating birth. This isn't just about finding more of them, it's about learning their life stories. From the violence of their ejection to the slow freeze of their surfaces, these missions will read the biography written in their light and their gravity. The dark spaces between stars are finally coming into focus, and they are far from empty. A planet's atmosphere is like its life story, but that story is told in light we can't see. For a rogue planet, it's told in the faint, thermal glow of its own warmth. That's the 11th mystery, reading a spectral signature in the dark, and the key is spectroscopy. Breaking light into a rainbow of colors, a spectrum, every chemical element, every molecule, absorbs light at specific wavelengths. It leaves dark lines in that rainbow. Like a fingerprint. Now, for a planet orbiting a star, this is incredibly hard. The star's light drowns out the planet's faint atmospheric signal. But for a rogue planet, especially a young, warm one, there's no star. Its dim infrared glow is all we have, and that isolation is a gift. We can point our most powerful telescopes right at it, collect its light without interference. Get a clean spectrum of its atmosphere alone. From that data, we can search for fingerprints, methane, water vapor, ammonia, carbon monoxide. Their presence, their relative amounts are profound clues. They tell a story of the planet's birth, its internal life, the ratio of carbon to oxygen in the atmosphere, for instance, that can reveal the temperature of the disk the planet formed from. Whether it was born close to a hot star or farther out in the cold. And the overall abundance of elements heavier than hydrogen and helium, what astronomers call metallicity. That points to the richness of the original stellar nursery. High metallicity might mean the planet formed in a busy, evolved region of the galaxy, a place enriched by many generations of stars. But the atmosphere also speaks of the present. Detecting certain molecules in unexpected combinations could signal active geology, chemistry driven from within. A surplus of methane alongside a lack of carbon monoxide, for example, that might indicate chemical processes reshuffling molecules in the atmosphere, maybe driven by internal heat rising from the depths. Then there's the most tantalizing possibility, chemical disequilibrium. That's when the atmosphere holds compounds that should react with each other and disappear. But they persist. On Earth, the simultaneous presence of abundant oxygen and methane is a powerful biosignature. Life constantly replenishes both gases. It keeps the atmosphere in a state geology alone can't explain. On a rogue planet, that disequilibrium would have a different source. Without sunlight for photosynthesis, any persistent imbalance would have to be powered by the planet's internal heat, or by exotic chemistry in its upper layers, and detecting complex organic molecules, the carbon-based building blocks of life that would push the boundaries of what we consider a living world. It wouldn't prove biology exists, but it would reveal a world that is chemically active, complex, a world where the ingredients and the energy for interesting chemistry are present and working. It transforms the rogue planet from a frozen statue into a dynamic chemical laboratory, its atmosphere a swirling canvas, where the basic rules of planetary evolution are being rewritten. In the endless night, that silent count in the dark leads to a deeper question. What is a planet really? The official definition comes from the International Astronomical Union from 2006. It says a planet has to orbit the Sun. It has to be round from its own gravity, and it has to have cleared its neighborhood of other debris. That first part, about orbiting the Sun, is profoundly solar-centric. It's a definition built from our own backyard, from our own star and its family. It works for us, for reclassifying Pluto for our textbooks, but it excludes every single rogue planet in the galaxy. By that definition, a world 10 times the size of Earth, with an atmosphere and hidden oceans, drifting alone for billions of years, isn't a planet at all. It's just something else, and that reveals a tension. We've defined a category of object not by what it is, but by where it is, by a relationship. It's like defining a child not by its own qualities, but only by the presence of its parents. The rogue planet challenges that. It pushes us to think in more universal terms, To define a planet by its intrinsic properties, by what it's made of, how it formed. Is a world defined by the light that falls on it, or by the geology churning inside? By the heat it gets from a star, or the heat it generates and holds onto itself? These nomads push us toward essence, not circumstance. They ask us to consider mass, internal structure, geological potential. Could a planet be any rounded body, below the mass for nuclear fusion that formed through core accretion? That definition would include the worlds in our solar system and the orphans in the void. It expands the idea of a world. We instinctively link a world with a sun. With days and nights, a horizon lit by a distant fire. But a rogue planet is a different kind of world, a world of perpetual interiority. Its drama is internal. Its energy comes from within. Its weather is driven by its own cooling heart. Any potential biosphere is sealed away, independent of any external light. It's a self-contained, sovereign entity in a way that Earth, for all its beauty, is not. We are dependent on our star. A rogue planet depends only on itself and the slow decay of its own atoms. That shift has practical consequences. It changes how we search, how we catalog, what we value. If we cling to the old, sun-centered definition, we might overlook the most numerous planetary-class objects in the cosmos. We'd be designing our curiosity around a cosmic minority, the worlds lucky enough to stay in a star's embrace. Recognizing rogue planets as true planets forces a more inclusive map. It suggests the familiar, sun-lit categories we know are just one chapter. The galaxy isn't just a collection of stellar systems. It's a deeper tapestry, woven with countless dark threads, threads that are worlds themselves, moving to a rhythm we are only beginning to hear. Eventually, the internal fire has to fade. A rogue planet's final fate is set by thermodynamics, and by time, it's a story of cooling. Over trillions of years, the radioactive elements in its core decay. They reach stable end products. The leftover heat from its formation, that violent beginning, finally radiates away. It goes out into the endless cold of space. The planet's geological heartbeat slows, then it stops. For a gas giant, the thick atmosphere might slowly precipitate. It snows down as exotic ices, building up on a frozen surface. For a rocky world, a subsurface ocean, if it ever existed, would finally freeze solid. The ice shell thickens. It thickens until it meets the rocky mantle, locking away any last remnant of liquid. The world becomes a uniform sphere, cold rock and ice, a perfect thermodynamic equilibrium with the cosmic background. It achieves a kind of absolute stillness. But its journey continues. Its path around the galaxy isn't a stable, forever orbit. Over timescales that dwarf the current age of the universe, subtle forces act. There's the gentle drag from the tenuous interstellar medium, the cumulative gravitational nudges from passing stars, from dark matter. These effects slowly erode its momentum. On a timescale of quadrillions of years, a rogue planet's orbit may decay. It may begin a slow, inexorable spiral inward, toward the supermassive black hole at the galactic center. That final descent would take eons, but it would end in a silent, dark plunge, a disappearance without a flash into the ultimate gravity well. Alternatively, its fate could be collision. The odds are astronomically small, given the vast emptiness, but given enough time, trillions upon trillions of years, even the most improbable events become possible. A direct impact with another rogue planet is the rarest of cosmic accidents. Two dark wanderers on independent paths for billions of years, finally intersecting. The release of energy would be titanic, but utterly unseen. A brief flash of light and heat in the perpetual dark, then a cloud of debris that would slowly cool and scatter. More likely is a slow, gravitational capture by another star. That leads to a new life in orbit, or a grazing encounter that tears the world apart, creating a new generation of smaller fragments to wander on their own. Yet the most probable end isn't a dramatic collision or a fiery plunge. It's simply endless drift. As the galaxy evolves, stars burn out, stellar systems dissolve. The great spiral structure fades. In the far, far future, the universe expands and cools. Galaxies become isolated islands of fading stars and dark matter. In that distant epoch, rogue planets may be among the last macroscopic objects left. Stars will have become white dwarfs, neutron stars, black holes. But these frozen, geologically dead worlds will still be there. Silent, dark, cold, they will outlast the stars that birthed them. They become the final monuments. Not to empires or civilizations, but to the simple, fundamental process of planetary birth itself. In a dark and quiet cosmos, they will be the last physical reminders that creation once happened here. That gravity once gathered dust into spheres, and that some of those spheres were set free. Their ultimate fate is to be the enduring fossils of a dynamic, younger universe, carrying the story of their origin into a future too distant for any eye to see. Science fiction has always gone to the dark between stars for its stories. Rogue planets were in our myths long before we knew they were real. They're the perfect stage, a world with no sun. It's a blank slate. Every rule we know just stops. Think of the planet in Alien, LV-426. Just a windswept rock, orbiting a star too far away for any warmth, and on it that derelict ship, like a fossil frozen there holding something terrible. The place itself becomes a character. Silent, hostile, completely isolated, it makes the crew's vulnerability total. A prison of ice and stone, light years from anyone. Then you have something like the wandering Earth. A different vision, collective survival. They turn Earth itself into a rogue planet. Fire the engines to push away from an expanding sun. The whole story is that audacious premise. A planet cut loose from its star. A generation ship for all of humanity. The drama is keeping that fragile bubble of life alive while the world hurtles through the dark. Facing cosmic hazards no one's ever seen. Here, the rogue planet isn't just the setting. It's the entire world. Its journey is the story. These stories touch deep archetypes. The rogue planet is the final frontier, completely disconnected. No rhythm of days and nights, no summers, no winters, no horizon lit by a sun you know. Just the permanent tapestry of the galaxy's stars. It becomes a powerful symbol. Isolation, being truly cut off. For a storyteller, it's a pressure cooker. Characters face external threats, but also the psychological weight of eternal night. Survival depends on internal resources, on technology, on will. Because the environment gives no solace, it's also a pristine lab for the unknown. In the deep quiet between stars, a rogue planet could preserve things for eons. Ancient ruins of unimaginable age, ecosystems that evolved in total isolation. Life that defies every law of biology we know. It becomes a cosmic attic. Holding relics from before the stars in our sky were born. That narrative role changes it, from a simple hazard to a vessel of mystery. It's where we might meet the truly alien. Not as invaders, but as forgotten relics, just waiting in the dark. This resonance goes both ways. Astronomical discoveries feed the mythology. They give writers new, scientifically grounded canvases. And the stories, in turn, shape our curiosity. They prime us to look at data from telescopes like Roman or Webb and feel wonder, not just calculation. They remind us that every point of light in the census, every microlensing event, it's not just a date, a point. It's a potential world with its own story. A story of ejection, of frozen seas, of a journey longer than human history. Science gives us the facts, but narrative gives those facts meaning. It connects the cold equations of gravity to our need for exploration. For myth, the evidence tells one story. These dark wanderers aren't accidents, they're a fundamental outcome, a product of the universe's rules. All the data points to one conclusion. Planet formation is messy. It's violent. For every world that finds a stable orbit, another gets thrown out. That's not a failure, that's the system. Chaos and gravity are the sculptors. Rogue planets are one of their most common creations. Our understanding has shifted. We've moved from speculation, from science fiction, to statistical certainty. The galaxy isn't mainly stars with their planetary families. It's a sea of darkness, thick with nomadic worlds. Bound systems like ours are just the visible islands in that dark ocean. It changes the perspective. Planets aren't defined by their relationship to a sun. They're defined by their mass, their formation, their internal geology. A world is a world, whether it's in starlight or sailing through eternal night. This reveals a hidden galactic ecosystem. These planets are part of it. They are not passive debris. They're active. Their combined gravity influences the motion of stars and clusters over eons. They act as gravitational shepherds in the dark. Their unseen presence shapes the galaxy's outer reaches. When one passes through a region like our Oort cloud, it can dislodge comets, send a shower of icy visitors inward. They're agents of change on timescales we're just starting to measure. Their diversity is staggering. Frozen, Earth-sized marbles, perfect time capsules. Young, glowing gas giants still cooling from their birth. Binary pairs dancing alone in the void. Some are geologically dead. Frozen relics. Others, warmed by radioactive hearts or the tidal pull of a captured moon, could host global subsurface oceans. Dark, silent biospheres, completely independent of any star. They carry the chemical fingerprints of their origins. This paints a universe far richer and stranger. A galaxy where the concept of home expands. It goes beyond the warm light of a sun. It includes the deep, internal warmth of a world that provides for itself. The companionship of a binary partner in the dark. The unimaginable patience of a journey that lasts longer than the lives of stars. Rogue planets aren't the exception. They're the silent, dark thread woven through the cosmos, a fundamental part of the story of how matter gathers and endures. They're a testament to a fact. In the universe, isolation isn't emptiness, it's a different kind of fullness, a different way of being a world. The rogue planet used to be a theoretical oddity. Now it's a cornerstone of modern astronomy. Its story isn't a sidebar, it's a central chapter. It speaks of violence and solitude, resilience and hidden potential. These dark wanderers show us that creation is inseparable from loss. For a world to find a stable home, others have to be cast out. That's the trade-off. It's written into gravity itself. They show us that solitude isn't emptiness. A world cut off from a star isn't a dead world. It can be a world turned inward. Powered by its own ancient heart. Holding oceans beneath a global shield of ice. It redefines resilience on a planetary scale. They challenge our most basic definitions. What is a planet? Is it a companion to a star, or is it something more fundamental? A rounded body of matter, below the mass for fusion, with its own geological story. By forcing this question, rogue planets expand our entire framework. They push us to think in terms of essence, not circumstance. A world is a world. Whether it basks in starlight or sails through eternal night. That shift in perspective is profound. It means our maps of the galaxy have been incomplete. We've been charting the lighthouses, but missing the dark ships that fill the sea between them. As our tools grow more powerful, this hidden population will come into sharper focus. The Nancy Grace Roman Space Telescope will transform microlensing from a statistical hint into a detailed census. We'll learn their true numbers, their masses, their distribution. The next generation of giant ground-based telescopes, with instruments like vortex coronagraphs, will analyze the faint infrared glow of the youngest wanderers. We'll read the chemistry of their atmospheres, looking for the fingerprints of their birth, the whispers of active internal processes. We may even find the spectral signatures of complex molecules. The kind that could serve as building blocks for chemistry, or perhaps in the warm depths of a subsurface ocean, something more. Their story is a reminder. A reminder that the universe possesses a strangeness and a wonder that consistently outruns our imagination. For every beautiful, sunlit world like our own, there may be countless others that have never known a sunrise. Yet they harbor their own forms of complexity and quiet drama. They are the unseen majority, the dark threads woven through the fabric of the galaxy. They ask us to listen not just to the light, but to the silence, and to the gentle tug of gravity in the dark.